Okay, everyone. So welcome to the May edition of the WARACI Camaraderie. Thank you all for coming along. My name is Terry Humphreys, and I'm your host for this evening. I'd like to start off by acknowledging the traditional custodians of the land we're meeting on, the Whadjuk Noongar people, and I wish to acknowledge their elders past, present and emerging. I'd also like to thank our sponsor, Chem Centre. Without them, we won't be able to have our networking and refreshments afterwards. And I'd also like to thank everyone who helps out with the Chemaraderies as well, like Keely on the front desk there, Matt as well, and Tamsin, who takes the recordings that we take and put it onto YouTube. So yes, it's so if you haven't missed any of these, you can always go back and watch them. On to the main event and the reason why we're all here this evening. We've got Professor Paul Lowe speaking from the School of Molecular Sciences at UWA on electron transfer within and through molecules, a more or less coordinated approach. So as you can see, his bio is jam-packed, full of awards and, fantastic career in chemistry. So as you can see, he won recently the RACI H.G. Smith Memorial Medal in 2020 and a J.G. Burroughs Award in 2024. And if you want to find out more about what he's been up to, you should look at the website and see. So please welcome Paul to the lectern.
All right, well, thank you very much, Terry, and thank you very much, Keely, Ben, to everybody for making the event possible. And of course, thank you all very much for taking time out of your very busy schedules to come along and be part of tonight. I'm truly grateful. I think this is one of the really wonderful things about our community, the interest and the engagement and the opportunity just to see what's going on in this particularly beautiful part of the world. This represented and afforded to us by these events is truly great. So thank you so very much. I will do my best to tell you some stories. I'll do my best to sort of try and illustrate some of the things that the really wonderful people in my group have been able to achieve, and I'm delighted to see some of them here. Elaine Goran-Sky was an absolute pioneer in my group, and actually her contributions to almost everything I'm going to be telling you about are really landmark. She's got a great deal of faith, trust, and then probably jumped off a cliff when she came to do a PhD with a synthetic organometallic group when she was really a high quality instrument scientist. And Elena's insights have really led us through to some of the things I'd like to tell you about this evening. So let's begin, and just to give me a little bit of a sense about where I'm pitching things. Can I just have a quick show of hands? Who's heard of Moore's law? And for those following on at home, that's about 3/4, 5/6 of the audience. So that's Gordon Moore. He was working with Fairchild semiconductors in the mid-60s. And this was about the point in time when integrated circuits were starting to be developed. And he sort of observed from a purely cost-based analysis that as you went down the line of integration, what had happened in 62 and 65 and 70, or projected out 70 I suppose, what he observed was that the cost of putting the number of transistors on a chip decreased until you hit a technology point, and then it became extremely expensive to put any more on. And what he did was, being a well-trained chemist, I suppose, he clearly wasn't a physical chemist, because he took the 4 data points that he had available and extrapolated. And Moore had sort of observed that we were roughly doubling component density in an economically viable sense about every 2 years. And he published that in a electronics magazine. It wasn't a peer-reviewed journal, it was just in a society mag, a little bit like publishing in chemistry in Australia. And that was taken as something of a incentive as a driver and industry target. And of course, that relationship has held true for 40, the last 70 years. It's really quite remarkable, driven through incredible advances in materials technologies, lithography, component stacking, design, really quite amazing feats of science and engineering in terms of driving the sorts of electronic devices that we all take for granted. But whilst we're sort of familiar, I suppose, with the development of electronic technologies and the pace of electronic technologies, we've still got Graham chasing me to get him a new laptop because the last one's not going fast enough. But it's the development of technology that's kept us moving ahead. To the point where we almost don't think about whether we will keep a phone for 20 years. A couple of years people want a new device, your laptop seems to need to be upgraded. So we're used to the incredible performance of these things. But if we dive back into the history, and this is a slide that was prepared by another PhD student, Marcos Gonzalez. And Santi went back and had a look at some parallel histories. And if we follow through what's going on with the semiconductor regime, we can see the first patents of the field effect transistor by Julius Lilienfeld. Things got a little bit distracted between the 30s and the mid-40s. And in 47, a group working in Bell Labs devised a device for controlling electronic current that bypassed Lilienfeld's original transistor design, which was based on planar electrons. So Bratton, Braden and Shockley won the Nobel Prize for the development of the point contract transistor. Lilienfeld holds is the name that's given to one of the American Physical Society prizes for his work in the area. Carrying on through, what are we sort of finding out? We're then finding out the integrated circuit technologies came through and around about the very late 50s into the 60s. Kilby and Noyce. Noyce actually passed away before the Nobel Prize could be awarded. Kilby got the prize in that area. Moore wrote his famous, what comes next, cramming more components. And then Moore and a group of others from Fairchild got together and decided this was a good area to be in. So for all the PhD students that are out there, if you have a good idea and you think you might be able to do something, don't be afraid to innovate. They went off and started their own company, much to the disgust of the owners of Fairchild. And, Intel, that was the company they founded. Has been going on ever since. So we can then sort of follow on through from that point to the modern day. But on the other side of the diagram, we've got what was happening in the chemical areas. And at the same sort of time that the Nobel Prize was coming out for the transistor effect, Arthur von Hippel wrote a piece on molecular engineering. And he was describing how it should be feasible to design materials that do things we want them to do from an atomic basis, from a starting point, using molecules which we can control the arrangement of atoms with exquisite precision through the agency of chemistry in order to do things. That was followed by Richard Feynman's famous lecture, There's Plenty of Room at the Bottom, which is often given acknowledgement as being the point where nanotechnology perhaps birthed. Again, von Hippel may have a certain claim into that area as well. And then at about the point in time when the first microprocessors were being released, Mann and Kuhn were starting to investigate the tunnelling of electrons through self-organised monolayers, and in this case fatty acids. Now, of course, we may choose to do this experiment with something other than a chain of alkanes, current understanding things. But what the Mann and Kuhn experiment did was that they were able to show that the tunnelling, or that the current, had an exponential decay with the length of the fatty acid comprising the monolayer. So essentially they showed that the current had a dependence tunnelling through molecules. And then a few years later, Avram and Ratner got on board. Avi Avram was a PhD student working with Mark Ratner. And Avram, from what I understand, basically came along to Ratner and said, hey, look, these guys are seeing tunnelling currents. Surely we can do something more than just tunnel an electron. And the Avram-Ratner diode was conceived with the idea of having a reducible centre, an oxidisable centre, which would make it easy to pass current through the device under bias in one direction, where you could easily reduce this TCMQ and oxidise the TTF. But if you wanted to pass current back the other way, you would have to impose a very significant bias in the opposite direction, a much greater bias, in order to reduce the TTF and oxidise the TCMQ before you could then get reverse electron transfer. So they developed a rectifier. To the best of my knowledge, that's never actually been made. There are many, many, many examples of donor acceptor rectifiers, don't get me wrong, but the Avram-Ratner, I don't believe, has ever actually been prepared. And then by the time we got into the early 2000s, crossbar assemblies with functional molecules assembled at the intersection points have been achieved. Fraser Stoddart was heavily involved in these sorts of work, and breakthrough of the year from Science magazine in 2001 was for wiring molecules. So whilst molecular electronics hasn't had the commercial impact of conventional semiconductor electronics, they have been running in parallel almost since their conception. So in terms of molecules, we have this opportunity to design incredibly functional material with exquisite precision. We can make a mole of molecules where each and every single one of them is exactly the same as every other. We can organise them on surfaces. We can interrogate them using a variety of radiation and techniques. We've got incredible control over our ability to assemble matter through chemistry. For a long time, molecules have been proposed as perhaps being the ultimately scaled electronic components. Now, I'm going to not sit here and tell you that we're going to make computers out of molecules. That was a thought, a dream, an ambition for a very long time, but I think we probably have to accept that molecules are not going to outperform silicon doing what silicon does very, very well. But maybe we start to think about what is it molecules do that the solid state don't, and then how we use that. But more to that to come. My point really at this stage is that we have now reached the stage of development where we can contact single molecules between electrodes. That's some of the work that Elena was doing, and I'll tell you a little bit more about that later. We can take monolayers. This is essentially the Kuhn experiment. And we can use nanofabrication techniques. This is an FEB, a focused electron beam type experiment, where we can deposit electrodes on top of monolayers in order to get patterns, write circuits. The reproducibility of the current that flows through those molecular devices is incredible. That was some work that was done with some colleagues at the University of Zaragoza. So we really have got quite an advanced fabrication platform that we can use in this area. Now, as I said, probably the trick is that we don't really want to be trying to outperform the chips that are in your laptops or your phones or your TVs or your fridges or your smart speakers or anything else that you might want to look around. But we start to ask the questions, what might we be able to do with these molecular junctions where we've sandwiched molecules between electrodes to achieve function which would otherwise be difficult to achieve with a solid state? We can start to think about flexible, biodegradable electronics. This was a review that was written in collaboration with a very good friend, Prashant Sona, at the Queensland University of Technology. Prashant is an absolutely wonderful individual. If you ever get a chance to see him speak, please do. He's vibrant, he's energetic, he's engaged, and he is one of the most imaginative people that's going around. We can look at using the fact that we have got molecular recognition. We're able to connect single molecules. We can start to think about using these junctions which are responsive to their environment. We all know that solution and environment interactions in solution are important in chemistry, so we can start to do chemistry, if you like, within junctions. And that then gives us an opportunity to follow what's happening between the electrodes as a function of the chemistry through the change in the molecular structure and hence the change in the tunneling current that's running on through. And this is a piece of work that came out of Nadine Darwish's group, and again I'd really like to acknowledge the camaraderie that Nadine and Simone and the guys over on this side of the river have given in terms of making Western Australia really the centre for this work in this country. And again, some of the things we've been able to do with our colleagues in Spain, we can now take molecular monolayers, we can put them onto flexible substrates, that's a PSS substrate, put down a monolayer, we can electrograft it to the polymer, top coat it with graphene in this case, and we can now start to prepare flexible, transparent monolayer devices. They'll support current, they're pressure sensitive as you squeeze the monolayer between them, and it really does open up a realm of possibilities that would be extraordinarily challenging to do with conventional silicon-based materials. All right, just to try and keep the physicists happy if we can, what are we trying to think about here? Don't think too much about these diagrams, except for the fact that we are going to be describing the probability of electron tunneling through a junction in terms of a transmission function. All the transmission function is an expression of that probability tunneling event. And so the plots that I've drawn here, these are really just the plots of the transmission function through some sort of arbitrary molecule as a function of the energy of the transmitting electron. And what we're seeing there are resonances, peaks in the transmission function, and those resonances occur when the energy of the transmitting electron coincides with an energy level of the molecule. In other words, we've got resonant transport, or if you want to think about it, we've aligned the Fermi energy of the electrode with the molecular orbit. And so it can tunnel straight through, much more probably than if it was off resonant. And so the value of the transmission function at the Fermi energy can be integrated to give us some measure of the conductance G. So if we know the magnitude of the transmission function at the Fermi energy, we can calculate conductance. There's another materials property that's probably more interesting than just pure conductance, and that's the Seebeck coefficient. And the Seebeck coefficient basically relates to the efficacy of the thermoelectric effect. It's the thermoelectric parameter. It's the parameter that describes the ability of a material to turn a thermal gradient into a potential gradient. So if you want to think about it in terms of the piezo effect, we're not turning electrical potential into a mechanical change or a Peltier cooler, where we're turning a voltage into a temperature gradient, we're turning a temperature gradient into a voltage. Think about how warm your electronics get when they're being used. If we had some way to harvest perhaps even 10% of that heat energy and recycle it, we could save masses of waste energy. The thermoelectric effect is the sort of thing that's still being used to power the Voyager spacecrafts. In that case, one side of the thermal gradient is deep space, the other side is a plutonium source, which is gradually decaying, and that's what power the Voyager system's going down. But thermoelectrics are turning that thermal gradient, between the polonium source, deep space, into the electricity that's still powering Voyager. I don't think they told anybody they were sending a little bundle of radioactive death into the stratosphere when they launched the Voyagers, but anyway, that's what they did. But the key point here is that we can relate, because of this differential, the slope of the transmission function at the Fermi energy to the Seebeck coefficient. So if we can know something about the way our molecules are performing, something about the way that they're behaving in terms of their transmission probabilities, as a function of ejected electrons, we can not only start to think about engineering molecules and electrical conductance, but we can also start to think about its materials properties. Too many words on the slide. the basic point is that if we start to think about these as HOMO and LUMO energies, well, we're very, very good as chemists at designing molecules which are going to be easier to oxidise or harder to oxidise or easier to reduce. We're very good at actually making chemical design choices, that wasn't me, making chemical design choices in terms of being able to tune electronic energy levels. So if we've got some control over the transmission function, we're going to have some control over materials properties. The only drama is, whilst I said we can go and make these junctions, and certainly we can, Elena will tell you that they are not exactly the sort of thing that everybody's going to be running off to do in the way that you'd run an NMR or an infrared. Wouldn't it be great if we could have a more convenient tool to prospect for these promising molecular electronic functions? That's what we're coming to. With apologies for the horrible green, because again, going back into the history of these things, way before we even started to think about solid-state electronics or nanotechnology, people have been playing around with charge transfer through molecules, represented through systems like Prussian blue. And I gather Jeff Reinders was through Curtin this afternoon talking about Prussian blue. Am I right with that? I'm looking for confirmation. I've got confirmation from the back of the room, and I've always trusted what Elena's told me. So the studies of charge transfer in molecules in terms of the field of mixed valence chemistry has been going on for almost as long as solid-state electronics or molecular electronics. Actually, hundreds of years before that, but let's just bring it on to where we started to get Marcus, of course, the late, great Noel Hush, Australian chemist, scientist, gentleman of extraordinary calibre. Hush and Reinders have worked in this area. They made immense contributions. So Australia takes a bit of a place in this as well. We can run our way through a whole variety of advances and theories that have been made about the spectroscopic understanding of electron transfer in molecules. So hang on a minute. If we really want to know about electron transfer in molecules, we've been studying electron transfer in molecules using spectroscopic methods for just as long as anybody else has been studying electron transfer through solids. So we've kind of got some potential handles in terms of photo-induced electron transfer and understanding of ground state electron transfer that we can get from spectroscopy. I won't rabbit on too long because I'll really blow my time out, but just to sort of say that we can treat these bimetallic systems linked by bridging ligands. If there's no interaction between the two sites, then the potential energy curves describing the electron localised on the left or on the right are non-interacting, and we call that class 1. Give you 3 guesses for what the other 2 classes are called. If we start to allow a little bit of mixing between the wave functions that represent the electron localised on the left or the right, we start to open up a little bit of a gap in ground state potential energy surface, which is double minimum, and an excited state. We can excite from the ground state to the excited state. That's obviously absorption of light. That relates to the coupling, whoops, let's find my pointer, which relates to the separation of those curves. And these are the sort of equations that Hush developed. And then, of course, if we extend to the stage where we've got complete delocalization, we lose that thermal barrier. These systems are now fully delocalized. These are class 3. And they're going to have quite distinct electronic spectroscopy and quite distinct infrared spectra as you go from readily identifiable sites to something which is neither oxidized, fully oxidized and fully reduced, the electrons being shared. So, where do we come into this now? That's a bit too long a background, but that's where we go. I've been interested in these carbon chains as conduits for electrons for a very, very long time, probably longer than I should have been. Partly because they are starting to get us on towards the missing carbon allotrope carbine. Carbine's the linear single atom chain of carbon. It's been calculated in all manner of forms. Polyion form is semiconducting, accumulated form with these persistent double bonds is metallic. The thermal conductivity is tunable by pressure. incredible tensile strength and wonder materials. But of course, if you imagine trying to create a chain of carbon with nothing but a chain of carbon, the ends start to become problematic. So we can only stabilise these models with end caps. And Harry Kroto won the Nobel Prize for the discovery of fullerene. He's been very forceful, wrote some very forceful commentaries about whether we should or shouldn't be calling model systems with end caps carbine. I think we all kind of miss Harry's opinions when it comes to much of this area. So anyway, so we look at systems like this and we start to think, well, these must look like really good wires. They must be of some interest to the whole field, so we'd really like to explore them. How are we going to go about exploring them? Well, one thing that we can do, so with apologies to Harry, is we can put some metal sensors on the end. And why might we like to do that? Well, we'd like to do that because the metal d orbitals are perfectly well set up to pi back bond into the chain, and we can start to get some metal representing the electrode injecting into the carbon chain. We can do that for the polyion form, we can do that for the accumulated form, and if we put two metals on each end, and now we might have a model for a junction, now you can start to see that we can potentially have models for these carbon chain devices. Vanity slide, forgive me, we've played with carbon chemistry for a very long time, but I want to draw your attention to the systems in the whole font. Those are our prototypical systems. Skip on through this one if you don't mind. Synthesis is remarkably easy. The redox chemistry is beautiful, and that then allows us to go and study these using spectroelectrochemical methods, where basically we take something like a conventional SpecAx solution infrared cell, and within the spacer we heat seal 3 electrodes, the working, the counter and the reference, fill the cell with the sample of interest and the oxidation state that it's native in, connect up the counter and the working, connect up the working and the reference, and now we have a 3 electrode cell. And then we can apply potential through a conventional potentiostat. Because this is only about 150 microns thick, we've got really good control over diffusion, and so we can electrolyse that small piece of sample, which is right in the beam path of the spectrometer, and we can go back and forth between the oxidation states as we wish. So basically, I'm lazy. We make one compound and get all the oxidation states for free. We can do this in the UV, we can do it in the infrared, we can do it in the near IR, we can hook it up whichever way we want. So here is perhaps the first example of our bimetallic with a little piece of carbon chain in the middle. Infrared spectra at the different oxidation states. I've only shown 3, but the others are available as well. Dan just keeps marching. We're looking at the C triple bond C, nice and weak in the starting point because it's a symmetric molecule. Second oxidation, we now see the C triple bond C marching to lower wave numbers as we start to evolve towards a more cumulonic form. Oxidise it again, we're now down to about 1750 wave numbers. We really have gone quinoidal in this case, and so we can play games not only with the structure of the molecule, but its the valence structure of the carbon chain. We go and have a look at the optical spectra. Sorry, what I would also say though is that because once we've taken one electron out, we don't have any distinction at all between the parts of the molecule, so this thing really is starting to look like it should be localised on the infrared time scale. And the near infrared transition, which corresponds to that nice transition that Hush predicted, follows pretty much all of the rules of Hush. We can talk about the little lumpy bump on the side if you really want to, but that relates to rotational dynamics in solution. So there's a good example. We can make a system, it's linear, it's conjugated, it's delocalised. Should be a good wire. Oh, there you go, it's delocalised. That's one for you, Graham. Done some DFT on these as well. And there's a lovely bit we won't talk about. So if we wanted to put these into devices and replace that organometallic redox probe with some electrodes, we took a silyl protected polyion, selectively deprotected in the presence of the gold, attached to the gold surface. We could then deprotect, revealing a chemically reactive terminal alkyne group. which we can then go off and surface functionalise and play with electron transfer rates and all the fun sorts of things that you like to do with modified electrodes. But we could also bring in a solution of gold nanoparticles, which are very prone to reacting with terminal alkynes. And now we can go and cap off this film of carbon chains, and we've created the first device which looks like it's got nothing but gold sandwiching carbon with gold top. So we might be getting close to something which starts to look like Harry's model. There is no end cap if you're going to give me that the metal electrodes are not end capping groups, and we start to get close to something that might be carbine. The more you press on it, the more the conductance goes up. This isn't actually any real distortion of the electronic structure. It really just represents the fact that we're starting to squish things out of the way and the tunnelling distance is getting weaker. But if we choose at an appropriate point before the model layer collapses, we get current flowing through the chains. It's great, but it's semiconducting, which kind of fits with the idea of the polyion structure should be a semiconductor. So we weren't too disappointed. What else can we do? Well, we can play some games with this transmission function. And I think if I just put to you a para-diethionyl benzene or a meta-diethionyl benzene, if I asked you which one's more conductive, para or meta, organic chemists in the room, don't let me down, guys, ladies and gentlemen. Which one would you think was more conductive, para or meta substitute? Go, Wes. Para. Got to be para. Yeah, it's conjugated. There's no tricks. But you give that same, and if you go to the meta, it's not conjugated, so it doesn't surprise you that there's not much current flowing through it. You give that problem to a physicist, and they go, "That's fascinating." And it's fascinating because the distance between the 2 points in the meta is shorter than the distance between the 2 points in the para. And so you've made the distance longer, but the conductance weaker, or if you like, you've made the distance shorter, and the conductance is worse. And they get really confused by that, and they go off and look at the transmission functions, and then they say, now we've got the idea. Because in the para system, all of the pathways, all of the electron pathways through that molecule result in the emergent electron wave functions being in phase. Whereas if you go through the meta system, the transmitting electron wave functions through the multiple paths emerge out of phase. They destructively interfere. So what we've got in this para versus meta is a room temperature, single molecule quantum filter. The electron that is transmitting is going through with complete quantum coherence. They get very excited and go off and write a Nature paper, and every organic chemist in the room cries. I'm not kidding you, they did. So, if you plot the transmission function, you see this destructive quantum interference dip, which results in the low conductance. But we can play games with that transmission by putting some substituents around. Now, this is work that comes out of another Australian product, Western Australian product, Solomon, who's now over in Denmark, DTK. And what Gemma and her crew showed was that if you insert a substituent, be it an electron donating or withdrawing group, in the 1, 3, 5 position, that sits on a node, it does absolutely nothing. But donor or acceptor groups in the 2 or 4 positions will shift the dip to the left or the right. That's representation from Mark Garner, who works with Gemma, one of their excellent papers in this regard. So we thought, well, hang on a minute. We can make mixed valent complexes that look like that rather easily, and we can make molecular junctions that look like that rather easily. So wouldn't it be nice to have a nice correlation to see if the predictions of quantum interference for junctions, A, do they hold in the junction, and B, do they hold in the mixed valence case? And indeed they do, and this is some work that comes out of a large number of students through the group, and particularly call out Dan Mazzucato, who did the work at the top in his honours year. Truly quite a stunning individual. And what Dan was able to do was to show that as we inserted in this case, the donating methoxy group into the 5 position, we really didn't do too much to the intervalence charge transfer band. Squeeze it into the 2 position, a little bit of enhancement, we might have done something there, but put it out in the 4 position where it's free to roam, and you've got to give me that intervalence charge transfer band has dramatically increased its intensity. And indeed, that same pattern of behaviour follows the conductance. This is log G over G naught. Very little change from the meta-substituted benzene in the case of the 5 position. A little bit of a shift in the opposite sense, which is what you'd expect from that methoxy group. It's struggling to get into conjugation in that pocket. But if we go and put the tuning group, quantum tuning group out in the 4 position, we go and increase the conductance by about an order of magnitude. So just inserting that methoxy group increases the delocalization in the molecule, and it increases the conductance. So we think we've kind of got something that starts to look like we might just about be able to use mixed valence chemistry as probes in molecular structure, molecular junctions. I'll skip over that. That's basically just sort of showing that it really does depend on the orientation of the group. That pocket is really very restricted, and the methoxy group struggles to actually get into conjugation with the pi system, which is why its effect is rather weakened. Okay, last story, and then let everybody get off to some beverages. We were playing around with these carbon chains. We've been playing with them for quite a while. This is some work that we've just put onto the archive, so I'll talk about it now. We took some gold-capped polyions because these gold complexes are actually very, very good at transmetallating to gold surfaces. So they're almost an ideal vehicle to transfer a carbon chain. We don't have to do the deep protection chemistry that we were using in the films when we started doing these experiments in 2017, 2018. And we could now do the single molecule junctions. And so Jared went off and made some of these compounds. Elena had a look at them together with Eloise Dixon, who was in the lab at the same sort of time. Elodie was probably hanging over doing crystal structures and making sure that everybody in the group was keeping things on track. And the first thing that Elena saw was, well, hang on a minute, we've got lots and lots and lots of these conductance features from these gold polyions. And they are incredibly long. So we did a little bit of thinking, a little bit of work, and what we think is happening is that the contact between the carbon and the gold is so incredibly strong that as we separate the junction, what we're doing is basically extruding gold atoms from the electrodes, and another carbon chain can then go and click itself in, and we basically pull carbon gold, carbon gold, carbon gold polymers as we pull. Well, that's really very good. We can identify the monomers, we can identify the dimers, and we have 2 points for the trimer. I'm not going to go and do a Gordon Moore and extrapolate that one. But that all looks very nice. There we go. We've got linear decay. That's looking good. That's what they should do. Molecules are getting longer. Conductance is decaying exponentially. Just boring, really. So then we made them longer. And that happened. In the case of the monomers, at about C12, there was a pronounced increase in conductance, which virtually now does not decay with increasing rate. It's completely different to what happens when you've got junctions formed with end caps. They just do the normal sorts of things. And the conductance, we're putting through about 0.6 G naught, about 0.6 of a metal atom contact through about 30 angstroms. If we try to model this using a polyion model, we get the black circles. That's the semiconducting system that we saw with the short chains that we assembled into the SAM structures. But if we allow the bond length alternation to equilibrate, in other words, if we start to allow the system to go quinoidal, a tight binding model predicts that's going to happen. Oh dear. The conductance curves decrease with increasing length, and then progressively increase to the point where we've almost gone ohmic through this carbon chain. We can prepare some model systems where we use nanoparticles in lieu of the electrodes, assemble the carbon chains between, and we can see from the Raman shifts the CC stretches are starting to go quinoidal. And so what we think over this about 3 nanometers that we're pumping, we don't have the semiconducting polyion form, that seems to be the dominant form for the shorter chains. But as we go longer, we've actually achieved the cumulonic form of carbine, which is the form that's then predicted to have metallic conductance. So we're reasonably confident, we hope. We'll see what the editors and then the referees may have to say about that. But it does look like we've got something which is getting pretty close to the predicted properties of carbine. So with that, I'll leave that one there. I've spoken a little bit longer than I perhaps might have intended, but I hope I haven't bored people too much. Lots and lots of people have been involved in the work over the journey. I am really just the person that gets to go around and talk to some incredibly talented people. Colleagues at Technical University Berlin were heavily involved in a lot of the mixed valence work. Very early on in my career, some wonderful colleagues, Jean-Francois Allais, Claude Lepant, the University of Rennes, and more recently in other work within Urban, Florence Mongeant. Richard Nichols has been an absolute inspiration to me. Richard took me under his wing when I was a young academic in Durham. Simon Higgins is another stalwart of that group, and one of their protégés, Andrea Bozzoli, is now a full professor in his own right. He's been a good mate, had an awful lot of fun, and he's been heavily involved in the carbon chain work. Pilar Ansanti at the University of Zaragoza, anything that's in film comes from work with them. Wen Jing at Xiamen was involved in the DQI tuning, and lots of our modelling of junctions comes out of Lancaster with the indomitable Colin Lambert and his protégés. Odi Alwadi is now in Babylon. Sarah Sakatash and Hatef Sadeghi have got their own positions at the University of Warwick. Highlighted, of course, are the UWA team. These are really the people that are present in the group at the moment or have made substantial contributions to the work that's being presented. I've tried to mention them by name as we've gone through the presentation. But with that, ladies and gentlemen, there is no more. From the other side of the river, that's the view looking back across. Thank you very much indeed for your time.
Well, let's thank Paul again for an excellent talk.